Hello there. This lecture is all about sampling distributions and how to use sampling distributions and something called the unit normal table that uses z-scores to figure out the probability of any given range of sample means. So in the previous chapter, we covered the z-distribution. And remember, the z-distribution always has a mean of 0, right? The z-score for the mean is always 0, and it always has a standard deviation of 1, because a score that's one standard deviation above the mean has a z-score of 1, for example. And remember, the z-distribution is the same shape as the population or the sample distribution that was used to compute those z-scores. We also looked at how to convert an x value into a z-score and vice versa. So to find the z, you would take the score minus the population mean divided by the standard deviation. To find x, you would take the z-score from the table for x, multiply it by the standard deviation, and add the mean. We also looked at how to determine the probability of selecting scores within specified ranges using z-scores and the unit normal table. So remember, you would take x, convert it into z, then look in the table to find the probability. Or to go the other way, if you were given a probability, you would take that probability, figure out z in the table, and then calculate x to figure out what score is at that specific percentile, for instance. So that's the past. Now we're moving on to the sampling distribution, which is not the same as the population or the sample distribution. So, although applying the concepts of z-scores and probabilities to single scores is great for the illustration of these concepts, in actual research, we rarely care about single scores, or in other words, a sample size of 1. We care about samples. So, instead of examining the probability of obtaining a score or a range of scores from a population, we are concerned with the probability of selecting a certain sample from the distribution of all possible sample means, or in other words, from the sampling distribution. Again, the sampling distribution, the distribution that we're working with, the types of values that we're working with, will represent all possible random sample means taken from a sample of a specific sample size from the population. And I'll really drill down into this concept in this lecture, so that'll start to make more sense. So now, because we are no longer working with scores, we're working with means, sample means. Instead of working with the standard deviation, which is the average distance between all scores and the mean to determine variability, now we're moving from the standard deviation as our measure of variability to the standard error. And the standard error is similar to the standard deviation, but is focused on sample means instead of scores. So now our measure of variability, or our spread, is going to be the standard error. And the standard error simply tells you the average distance between all sample means of a specific sample size and the population mean. Or in other words, how much differences you would expect to see between any given sample mean and the population mean just due to random chance. So there's problems with samples. Samples are variable. There's different individuals with different scores and different sample means in these different samples. Thus, the sample mean often differs from the population mean, and the sample means often differ from each other. If you took two random samples, even if the sample size is the same, chances are those sample means will not be the same. And this gets at sampling error. And sampling error is just the discrepancy between sample mean statistics and population parameters. So the standard error is a measure of sampling error, and it tells you the difference to expect between the mean of any given sample of a specific sample size and the population mean just due to chance. And it's a very important concept for the sampling distribution. So this lecture will really focus on understanding what is a sampling distribution, what are the properties of the sampling distribution, and what is the standard error. And then you'll use that knowledge to determine the probability associated with specific sample means. All right, so just a quick outline of what I'll be covering, and I've already kind of mentioned this. So demonstrating the sampling distribution. Luckily, there's this thing called the central limit theorem that makes it so that we don't have to do the demonstration of the sampling distribution that I'm going to show you. But I'm showing you that demonstration so you understand the sampling distribution a little bit better. But as you'll see, it can be quite tedious to manually construct the sampling distribution, and the central limit theorem gives us rules to follow so that we don't have to go through that process. Then I'll look at the impact of the standard deviation and sample size on standard error. Remember, standard error is just a measure of sampling error, telling us how much difference we would expect to see between any given sample mean drawn from the population and the population mean itself. Then I'll do a quick terminology summary just to familiarize you with some of the terms that we are using and that we've used throughout the lecture. Then I'll get into how the sampling distribution and the empirical rule are related. Remember, you saw the empirical rule before when it looked at specific proportions associated with values in the data set in the normal distribution based on the mean and the standard deviation. Well, now the empirical rule is going to be based on the population mean and the standard error. Then I'll just give you a quick summary of all the distributions you've learned about this semester, including the sampling distribution. And then I'll do several example problems to show you how to use the sampling distribution and the unit normal table to identify the probability of specific sample means. So for any given population, there are typically a huge number of samples that can be drawn from that population. Normally, one thinks of sampling from relatively large populations, right? Remember, the population is everybody or everything that you're interested in. Typically, that's pretty large. But the concept of sampling distributions can be illustrated with a very small population and a very small sample size. So, for our purposes for this, we are going to assume that sampling distribution is based on random sampling with replacement. So, for instance, let's say this is our population, and let's say that these represent, I don't know, a number of children. So we're looking at the number of children among 3 of our employees. And let's say we only have 3 employees, and one has 3 children, one has 4 children, and one has 5 children. Well, for any given random sample that we took of 2 employees, we could technically, if we're doing random sampling with replacement, we could take this person, put him back, and then take him again. So we could get the same person twice, right? Because we're doing sampling with replacement. So keeping that in mind, if you were to construct every single possible sample of 2 from this population, you could get the same person twice, right? So you could get the 3, put them back, and then get the 3 again. So when you're looking at the distribution of sample means, in this example, we want to look at every single possible sample mean that we could get from a sample size of 2. And there should be a little bar above this x. It's not very clear, but this represents the mean. All right, so every single possible 2-number combination from this population to get all the possible samples that you could get. So we could have 3 and 4, 3 and 5, 4 and 3, 4 and 5, 5 then 3, 5 then 4. Then we could also have a 3 and a 3, a 4 and a 4, and a 5 and a 5. So this is the exhaustive list of all the possible 2-number combinations, sample size of 2, that you could get from this population. So the way that you get your distribution of sample means is you calculate the mean for all of those samples. So 3 plus 4 is 7, divided by 2 is 3.5. 3 plus 5 is 8, divided by 2 is 4, all the way down. Then, if you want to get the distribution, remember the distribution is based on a frequency distribution table and then putting that into a graph. So, how many means of 5 did we get from all these possible samples? Just 1, right? So 1 is the frequency of a sample mean of 5. 2 is the frequency of a sample mean of 4.5, right? There's 2 4.5s, and so on and so forth. You know about frequency distributions already. And then I went ahead and calculated the probabilities associated with each sample mean. So what this is saying is that if you randomly took a sample mean of 2 from this population, there would be essentially an 11.1% chance that that sample mean would be a 5. If you randomly selected, right, with replacement, 2 people from this population, you would have a 22.2% chance that that sample mean would be 4.5. And all the way down the same interpretation. So once you plot these into a frequency distribution graph, you would see that you have a normal distribution here. The bulk of your sample means will be right at the population mean, and then as you get further from the population mean, those sample means are going to be less commonly occurring. Again, I'm never going to ask you to do this because there's something called the central limit theorem that makes it so that we don't have to do all this to calculate the things that I'm about to show you. All right, so here is that sampling distribution that we were looking at before, right? All the possible samples of 2 taken from this population and the means for those samples. Now, luckily, you don't have to do all of this to figure out the mean of the sampling distribution, because the mean for the sampling distribution is always equal to the population mean, which is a wonderful thing, right? So I'll show you how you can get the mean from the sampling distribution manually. You can add up all those means and find the mean of the means, right? So you add up all these means, you get 36, and then 36 divided by 9 samples tells you that you have a mean for your sampling distribution of 4. That is the same as the population mean. And that's covered in central limit theorem, but I wanted to demonstrate it for you here. Okay, now there's 2 ways to calculate the standard error. This way, I'm just showing you for description purposes to help you understand that the standard error is simply the standard deviation for the sampling distribution. This is the formula that we'll be using in practice, and you see you get the same answer. All right, so the first way to calculate the standard error, the one that's more conceptual and less practical, is you can basically look at, remember the standard deviation for the population, that formula is the square root of the sum of squares divided by n. Well, for the sampling distribution, it's the sum of squares divided by the number of samples, and you take the square root of that. But before we can do this calculation, we need to know the sum of squares. And remember, the sum of squares formula that you used previously when you were working with scores was the sum of x squared minus the sum of x quantity squared divided by n. Well, now we're just replacing x with the mean, right? We're done with scores. We care about means now. And now n represents the number of samples. So, if you've already sketched this out, you can quickly say, all right, let me square each one of my means. So I did that here. Add those together. That gives you the first value for the sum of squares. Then you're subtracting the sum of all the means, 36 squared, divided by, we have 9 samples. So you have 147 minus 36 squared, 1,296 divided by 9. That becomes 147 minus 144, and you have a sum of squares of 3. So then, just like you would do with the standard deviation formula, you plug that sum of squares into the standard error formula, divide it by the number of samples, and you end up with the square root of 3 divided by 9, which becomes the square root of 0.333, and you get a standard error of 0.577. So what this tells me is that just randomly, just due to random chance, any random sample that I took from this population with a sample size of 2 would probably be about 0.577 points. The mean for that sample would be about 0.577 points away from the population mean. That's the difference that we expect to see just due to chance between our sample mean and our population mean. But there's a much simpler formula that you can use to find the standard error that doesn't require you to go through and find every single possible sample mean. So you could just take the standard deviation for the population, 0.816, divide it by the square root of the sample size, and sample size is 2. That becomes 0.816 divided by 1.414, and you get the same standard error. Again, I was just showing you this process to show you that the standard error is essentially the standard deviation of the sampling distribution, or the standard deviation of every single possible sample mean of a specific sample size that you could get from a population. Now, there's a quick way to figure out how many possible samples can come from any given population based on the sample size. And that's to take this population size to the exponent of the sample size. So in this example, our population consisted of 3, and our sample size was 2. So 3 squared is 9. Now imagine in a more realistic situation. Let's say that we had a sample or a population size of 1,000, and we wanted to take sample sizes of 25. Well, that would be a very, very, very large number, right? So you can imagine that if you were going to do this process when you had a more realistic population and a more realistic sample size, this would take so much time. It would be painful. And luckily, you'll never have to do this. Again, I'm just showing you this so that you understand how you get the distribution of sample means, or the sampling distribution, and what it actually tells you. Every single possible sample mean of a specific sample size from the population. Now here's an alternate situation when you have random sampling, but we don't assume replacement. So instead of, if this is still looking at, the number of children among 3 employees, once we select the person who has 3, they're in our sample. They don't get replaced before we make our next selection. So you're never going to have the same number twice. And you're not going to consider different combinations of the two numbers when you're doing sampling without replacement. So you won't have a situation where you have, oh, I have a 3 and a 4, but I also have a 4 and a 3. Because without replacement, you're assuming that once this person's already been selected, they can't be selected again, and you're not going to have a situation where you have these two different samples because this person and this person are already in a sample. They're not being replaced. Also, you're not going to have a situation where you have the same number twice, right? The same person being selected twice in this example. So when we're doing sampling without replacement, you would simply just go, okay, 3 and 4, that's one possible combination. 3 and 5, that's another combination. And then 4 and 5. And to figure out the number of possible samples that you could get when you're doing sampling without replacement, you can use this thing right here. So this is actually called the counting rule for combinations. This was in the binomial distribution chapter. It's part of the binomial formula, but I didn't make you responsible for it. But here it is to figure out the number of possible samples that you could get with a sample size of 2 and a population size of 3. You could do this formula right here. So you would take the population size factorial divided by the sample size factorial multiplied by the sample or the population size minus the sample size factorial. Factorial just simply means you multiply all the numbers leading up to that number with the exception of 0. So 3 factorial is 3 times 2 times 1. 2 factorial is 2 times 1, and then 3 minus 2 gives you 1, and 1 factorial is just 1. So 3 times 2 times 1 gives you 6. 2 times 1 is 2. 6 divided by 2 tells you 3 samples. Don't worry too much about this. I'm just showing it for demonstration purposes. So just like before, to find the mean of the sampling distribution, you take every single possible sample that you could get from the population, add those sample means together, 12 in this case, divide by the total number of samples. So we would have 3.5 plus 4 plus 4.5, all the possible means from all these possible samples added together, divided by 3, total number of samples, and you get 4. And this is great because 4 is still equal to the population mean. So luckily, the mean for the sampling distribution and the population mean are still the same, and there's still a simpler version of the formula to use to calculate the standard error. So I didn't even go through and show the sum of squares version of this formula just because you're never going to use it. And in fact, you're never going to use this because I'm never going to give you a situation without replacement. I just want to show it to you so you understand that there's differences in the distribution when you're doing with and without replacement. But when you're finding the standard error, when you have a situation where you're random sampling without replacement, you simply use the traditional formula for the standard error, so the standard deviation of the population divided by the sample size. In this case, it's still 0.577 because we're still using the same population and sample size. And then you just add this little correction formula to it. So you multiply it by the square root of the population size minus the sample size divided by population size minus 1 to give a little bit of a downward correction. Now, that correction is there because we expect less variability with sampling without replacement than when we do sampling with replacement. So this corrects for that, less variability. Because we're not doing replacement, right? We're doing sampling without replacement, so we don't expect as many samples, we don't expect as many differences. So we have less variability expected when we have random sampling without replacement. So again, I will not focus on random sampling without replacement. And here's why. No matter what, Even if you're not using replacement, you do not need to worry about this correction formula as long as your sample size is less than 5% of the population size. And this is quite typical. We're typically working with really large populations, and typically our sample size does not exceed 5% of our population size. So if that's the case, you don't have to worry about the correction formula. Now let's get to central limit theorem, which is the magical concept that makes doing all this stuff pretty much unnecessary. So the central limit theorem makes it possible to understand the characteristics of the distribution of sample means, or the sampling distribution, without taking hundreds or thousands of samples, which you would need to do if you had the realistically, large populations and large sample sizes. So the central limit theorem identifies the characteristics for the distribution of sample means, or the sampling distribution. Those two terms can be used interchangeably. It defines those characteristics for any population, no matter what is the population size, shape, mean, or variability. So this is a consistent rule that you can always apply to any sampling distribution. And the central limit theorem identifies the three basic characteristics of the sampling distribution. The first characteristic is shape. So what is the shape of the sampling distribution? And it depends on two factors. So the first factor is the shape of the population distribution from which you sampled. If you have a normally distributed population, then the distribution of sample means will be normal, no matter what your sample size is. Even if you have a sample size of 1, the sampling distribution of the mean will be normal because when you have a sample size of 1, it's an exact copy of the population distribution. Sample size is the second factor that dictates the shape. So remember, if you have a normally distributed population, then your sampling distribution will always be normal. Even if you have a population that you're sampling from that's extremely skewed, non-normal distribution, the sampling distribution of the mean will still be approximately normal given a large enough sample size. So as long as you have a sample size of 30 or more, you're going to have a normal shaped sampling distribution, even if your population distribution is skewed. So greater sample sizes help ensure that the sampling distribution of the mean is normal. And this is important because we're going to be using the unit normal table to estimate probabilities of samples. So that way, there's no need to hand calculate probabilities after finding all the possible means, right? Again, we don't want to have to find all those possible means to hand calculate those probabilities like you see that I did here. We're going to be using the unit normal table to figure out those probabilities. And the unit normal table relies on a normal distribution. So it's wonderful that in most cases we have a normal sampling distribution because then the unit normal table will be accurate. So if you think about it, we'll always have a normal sampling distribution as long as the population distribution is normal, or no matter what the population distribution looks like, as long as our sample size is 30 or greater, we're going to have a normal shaped sampling distribution. So think about it. What two conditions would have to be met to have a non-normal sampling distribution? So what two conditions would make us not so confident about using the unit normal table to identify probabilities? Think about it for a second. All right. So the only way that you can have a non-normal sampling distribution is if you have a population distribution that's not normally distributed and you have a sample size less than 30. All right, so that's shape. So this prevents us from having to figure out all the possible sample means of a specific sample size from the population and then count the frequency of those and draw a nice pretty graph, because we know the shape's going to be normal as long as we have a normal population distribution or our sample size is 30 or greater. Then the central tendency piece of central limit theorem. I already got into this. Remember, I showed you even if you take all those sample means and find the mean of those means, the mean of that sampling distribution is always going to equal the population mean. So still, we do not have to go through and find all those means to know that the mean for our sampling distribution is, because we know it's equal to the population mean. Now for variability. So the central limit theorem also talks about the variability of the sampling distribution. And remember, the variability that we use for the sampling distribution is the standard error. And the standard error is equal to the standard deviation of the sampling distribution. And the standard error tells you the standard or typical distance of any single sample mean from the population mean. It tells you how well any sample mean of a specific sample size should estimate the population mean. It tells you essentially how much sampling error there is to be expected by chance. So if you have a really large standard error, then your sample means are scattered across a wider range. So there's going to be expected to be bigger differences in sample means from one sample to another, and also more differences between any given sample mean and the population mean. If you have a smaller standard error, then that means that your sample means are close together, and that samples are going to typically have closer means, similar means, and also sample means that are closer to the population mean. Also, if you think about it pictorially, if you draw out a sampling distribution with a larger standard error, you're going to have a fatter curve. The means are less consistent. If you draw the distribution with a small standard error, you're going to have a skinnier normal curve, and your sample means are more consistent. Same type of interpretation that we had for standard deviation. So now let's look at the impact of the standard deviation and sample size on the standard error. So if we look at the formula for this, and you think about how fractions function, if you have a larger number in the numerator, everything else being held constant, the denominator is not changing, but as long as you have a larger number in the numerator, you're going to have a larger value overall. In this case, if you have a larger standard deviation, you have a larger standard error. If you have a larger value in the denominator of a fraction, then the overall value is smaller. So as long as the numerator is being held constant, if you're dividing by a larger number, you're going to have a smaller number here. So think about it. Let's say that the standard deviation is 10. And let's say that we want to know the standard error if our sample size was 100. Well, 10 divided by the square root of 100, 10 would be 1. Well, let's say that we take that sample size down a little bit. And now let's say that our sample size is 25. Standard deviation is still 10. 10 divided by the square root of 25, or 10 divided by 5, would be 2. So when you have a larger sample size, you have a smaller standard error. When you have a smaller sample size, you have a larger standard error. That's the mathematical interpretation of this. But let's think about it in terms of conceptual. Remember, this represents the standard deviation for the population, represents the spread of scores in the population. So if you have very, very different scores in the population, chances are any given sample mean that you take is probably going to be very different from any other sample mean that you take because the scores are just all over the place. So higher standard deviation in the population, scores are very different, more spread out. You would expect your means to also be more spread out. Lower standard deviation, the scores are closer together in the population. You would expect that any given sample mean taken from that population would be pretty similar to the population mean because the scores are really close. So you'd have a smaller standard error. Conceptually, the sample size. We have already discussed that larger samples tend to be a more accurate representation of the population. So if you have a larger sample size, you're expecting less error between your sample mean and the population mean. If you have a smaller sample size, it's probably a less accurate representation of the population, and you're expecting larger differences between sample means of a smaller sample size and the population mean. So just a summary of the terminology that I've introduced you to. So sampling distribution, that's the distribution that we're working with now. So when we draw our graph, our x and y axis, and we're plotting our normal curve, the values along the x-axis no longer represent scores. They represent every possible sample mean of a specific sample size that could be randomly drawn from a specific population. Or in other words, going way back to the beginning of this lecture, they represent all of the possible sample means. And then the y-axis represents the frequency or the probability of all those possible sample means that could be drawn from the population. Also, the sampling distribution can also be referred to as the distribution of sample means. These two things mean the same exact distribution. Then the mean of the sampling distribution is equal to the population mean, and we refer to the mean of the sampling distribution as the expected value of the sample mean if the sample actually represents the population. Then the standard error, which I talked about in length, that is the expected sampling error, or the typical or expected or standard difference that you would expect between every possible sample mean of a specific sample size and the population mean. And if that sample is an accurate representation of the population, then you would expect that your sample mean would fall within one standard error of the population mean. Now let's take a look at the empirical rule. So you've seen this before, but the last time you saw this, the frame of reference was the population mean, which is pretty much the same thing that we've got going on now because the mean of the sampling distribution equals the population mean. And in this case, we're saying our population mean is 20. And the z-score for the population mean was equal to 0. That has not changed. But what has changed now is that the measure of spread is the measure of spread of means, not scores, and it's the standard error. And here's a summary of the calculations for the standard deviation, or sorry, the standard error, and for z-scores now. So to find the standard error, I showed you this formula before. You take the standard deviation of the population divided by the square root of the sample size. If we're working with a situation where our population has a mean of 20 and a standard deviation of 10 and our sample size is 4, we end up with 10, right? Our standard deviation of our population divided by the square root of 4, the square root of our sample size. This becomes 10 divided by 2, and our standard error is 5. So when we're plotting out our distribution, for every 5-point increase in the sample mean, the z-score increases by 1. Because 25 is one standard error above the population mean. 30 is 2 standard errors above the population mean. And then as you go 5 points, or 1 standard error, below the population mean, your z-score decreases by 1 point. So 15 is 1 standard error, or 5 points, below the population mean of 20. 10 is 2 standard errors below the population mean of 20. And remember, we have predictable probabilities associated with any given sample mean now based on the population mean and the standard error. So 68% of any possible sample mean that you could possibly draw from this population, 68% of those means will fall between 15 and 25, within one standard error of the population mean. And 95% of those possible sample means will fall within 2 standard errors of the population mean, or between a mean of 10 and 30. Same sort of thing that you looked at before, only now instead of looking at scores and the standard deviation, we're looking at sample means and the standard error. And just like before, only 2.5% of now sample means will are more than 2 standard errors away from the population mean, and only 2.5% of sample means will be more than 2 standard errors below the population mean. Now the formula for the z-score has changed. Instead of being x minus the population mean divided by the standard deviation for the population, it's now the sample mean minus the population mean divided by the standard error. So we're still comparing the observed difference to the difference you would expect to see just randomly. But now we're looking at the observed difference between 2 means, the sample mean and the population mean, divided by the difference you would expect to see, or the common difference between sample means. Then if you wanted to find the mean based on this information, you could take the z-score, multiply it by the standard error, and add the population mean. So this is similar to finding x based on this information, where we took z times the standard deviation plus the population mean, only now we're working with means and standard errors instead of scores and standard deviations. So another thing, just like the example that we looked at for the empirical rule in the other lecture looking at z-scores, where we were concentrating on just scores and not means, as your sample mean gets further away from the population mean, the absolute value of the z-score gets larger, right? Because it's more standard errors away from the population mean. And as your sample mean gets further away from the population mean and the absolute value of the z-score increases, you also have a lower frequency associated with those sample means, which corresponds to a more rare sample mean that has a lower probability. So as you move out away from the sample or the population mean, your absolute value of your z-scores increase and your probabilities decrease. Because think about it. A sample mean of 4 has a z-score of, sample mean of 40 has a z-score of 4. And if you go up to the part where that meets the frequency distribution graph right here, that's a really low frequency. That's a really unlikely occurrence. Whereas a sample mean of 25 that has a z-score of 1, if you go up and find where that connects to the normal curve, it's a high frequency part of the distribution. It's likely to get a mean of 25 just due to chance from this population. Just like before when we were saying that any score that has a z-score that's 2 or more standard deviations away from the mean, we call that extreme. Now we say any sample mean that's 2 or more standard errors away from the population mean is considered extreme. So if you calculate the z for your sample mean and your absolute value is 2 or more, you can say that it's an extreme sample mean. It's extremely unlikely. All right. Now, summary of distributions. So this is just kind of succinctly putting it all together, all the distributions that we've talked about throughout the semester. So the population distribution includes all of the scores from every individual in the population. The sample distribution includes all the scores from the sample. And now the sampling distribution includes all the means from all possible random samples of a specific sample size taken from the population. For the population distribution, it could be any shape, typically normal. For the sample distribution, it's kind of a crapshoot. It could just be any shape. It's hard to tell. If you have a larger sample, it's probably going to be closer to normal, but it could be any shape. Then remember, central limit theorem tells us that the shape of the sampling distribution is normal if the population is normally distributed. And even if the population distribution is not normal, it's approximately normal as long as our sample size is 30 or greater. Then the measure of central tendency here, or in other words, the one we're most concerned with is the mean. Here's the formula for the population mean. Add all the scores, divide by the population size. For the sample mean, add all the scores, divide by the sample size. And then for the mean of the sampling distribution, you could take the sum of all the means for all possible samples of a specific sample size and divide it by the number of samples, or you could just say, I know it's equal to my population mean. Then variability. So this is the standard deviation of the population, the spread of scores in the population, the sample standard deviation, the spread of scores in the sample that's meant to estimate the spread of scores in the population. That's why we do this little n minus 1 the denominator, right? We bump it up a little bit so that it's higher because we know that the sample standard deviation tends to underestimate the population standard deviation. So we bump it up so that it's a closer estimate of the population standard deviation. Then we have the variability for our sampling distribution, the distribution that we care about now, which is the same thing as the standard deviation of the sampling distribution, and now we call it the standard error. This is the spread of score, or spread of sample means in the sampling distribution instead of the spread of scores. Then our z-scores. So for the population, we would take the score minus population mean divided by the standard deviation for the population. If we were trying to find a z-score within a sample, we would take the score minus the sample mean divided by the sample standard deviation. And now we are taking the sample mean minus the population mean divided by the standard error. I know it's kind of hard to see. There's like a little slight tick mark there. That's a mean, not a score. Little line above it. So now I'm going to work through some example problems to show you how to determine the probability of a specific range of sample means. And this is really similar to what you did when we were looking at probabilities of scores. Only now we're not converting x into z, we're converting a sample mean into z, and we're using these formulas. So you'll first need to compute the standard error using this formula. Then you'll plug that into the z-score formula in the denominator and divide the difference between the sample mean and the population mean by that standard error to find z. Then we will take z and locate the probability that we're looking for in the unit normal table. And we're still going to draw pretty pictures to determine, are we looking at a body, are we looking at a tail, are we looking at a mean to z. Alright, so let's take what you learned about the sampling distribution and z-scores to determine how to find the probability of a specific range of sample means using z-scores and the unit normal table that represents the sampling distribution. Alright, so the population of drivers has a mean of 10 and a standard deviation of 5 speeding tickets. So if we randomly select, and for our purposes, we're always going to assume that we're randomly selecting with replacement. So if we randomly select 100 people from the population, 10 people from the population, how well do we think that that sample mean will represent the population? And then the second one, same thing. If we randomly select now a sample of 400 people from the population, how well do we think their sample mean will represent the population mean on average? So if we are wanting to know how well, on average, the sample represents the population, what am I asking for? Think about it for a second. So hopefully you were able to identify that I'm asking you for the standard error, which is equal to the standard deviation divided by the square root of the sample size. All right, so let's go ahead and figure out the standard error when we have a sample size of 10. So this would become standard deviation is 5 divided by the square root of the sample size, square root of 10. 5 divided by, well, the square root of 10 is 3.162. 5 divided by 3.162 is 1.581. So on average, we would expect that any given sample mean taken from 10 people out of this population would be about 1.581 points away from the population mean. So what we really could say is, if you think about the empirical rule and the fact that 68% of scores or sample means will be within one standard error of the population mean, we could say that we are likely to overestimate the number of speeding tickets up to 10 plus 1.581 or 11.581, or to underestimate the number of speeding tickets down to as low as 10 minus 1.581 or to 8.419. So we would expect that with any given sample of 10 people from the population, that their sample mean would be between 8.419 and 11.581. And if we drew this out in our sampling distribution frequencies, these represent sample means. Actually, let's just represent the sample means. All right, so in the middle we have our population mean. Remember, the population mean is equal to the mean of the sampling distribution, and it's always in the middle. And then we would have a situation where we have most scores falling, so plus 1 standard error would get us to 11.581, and minus 1 standard error down to 8.419. And if we calculated the z-scores for those, we would have -1, 0, and +1. And remember, according to the empirical rule, most means, 68% of means, fall within one standard error of the population mean. This is going above and beyond what this question is asking for. All I asked for was how well on average will the sample represent the population. I'm simply asking for this. But it doesn't hurt to go further into detail. Now what if we were looking at a scenario where now the sample size is 400 and we want to know on average, how much sampling error can we expect with a sample size of 400? Or in other words, what's the standard error for a sample size of 400? All right, so the standard error is still equal to the standard deviation divided by the square root of the sample size. And our standard deviation is still 5. We're still working with the same population. But now our sample size is 400. So this becomes 5 divided by, well, the square root of 400 is 20. And now we have a standard error of 0.25. So now we could say that we are likely to be off by 0.25 tickets with our sample mean estimation. So we're likely to overestimate the number of speeding tickets up to 10 plus 0.25 equals 10.25, or to underestimate the number of speeding tickets down to 10 minus 1 standard error, 0.25, or 9.75. So if we round this, we're still looking at 10, right? 10 rounds to 10 and 9.75 rounds to 10. So we have a pretty darn close estimate of our population mean when we have a sample of 400 versus when we have a sample of 10. Let's go ahead and draw this distribution just to give you practice looking at these things. So we've got our means, we've got our z's. This is going to be a skinnier sampling distribution because our standard error is smaller. Our mean for our population is still in the middle. It still has a z-score of 0. But now we're looking at 10.25 and 9.75 representing the middle 68% of the distribution. That's one standard error above and below the population mean. It's kind of hard to see. Plus and minus 1 standard error. So, when we have a sample of 400, we have a pretty darn good estimate of the population mean versus a sample size that's smaller, like 10. And that's because we tend to expect that larger samples are going to be a more accurate representation of the population and have a smaller standard error. So this helps demonstrate the relationship between the sample size and the standard error. As the sample size increases, the standard error decreases, and we expect to have less sampling error with larger samples. Now let's do an example where we change the standard deviation. So we're still working with a population of drivers that have a mean of 10 speeding tickets, but now the standard deviation is 20 speeding tickets. And we're still randomly selecting a sample of 400, and I'm still asking you, how well on average will the sample represent the population? Or in other words, what is the standard error? So, drawing out my formula here. 20 is our standard deviation, and we already identified that the square root of 400 is 20, so we have 20 divided by 20, and we end up with a standard error of 1. So with a sample of 400 drivers, our estimate of the population average of speeding tickets would be off on average by plus or minus 1 ticket. So we're likely to overestimate the number of speeding tickets to 11, or underestimate the number of speeding tickets. Oop, look, I got ahead of myself. 10 minus 1 is 9. So we're thinking between 9 and 11 speeding tickets will represent that middle 68% of the distribution. So let's go ahead and draw this out. Just for kicks. Again, this would be what I would be asking for if this was how the question was framed. But if you're asked for the range of values that you would expect, then I'd be looking for something like this. So we've got our means. Population mean is in the middle, z-score of 0, and then we have 11 and 9, negative 1, positive 1. So this would be minus 1 standard error and plus 1 standard error. So we would expect that 68% of any possible sample mean from 400 people from this population would fall between 9 and 11. Now check this out. The standard error here is much larger than the standard error here. And the only difference is the standard deviation for the population. So when you have a larger standard deviation for the population, you have a larger standard error. Again, the scores are more spread out, so you expect that the means will also be more spread out. You have a larger standard error. So that demonstrates the relationship between the standard deviation and the standard error. So you could see that with a larger standard deviation, the margin of error increased from 0.25 with a standard deviation of 5 to 1 with a standard deviation of 20. All right, now let's get into using the unit normal table to figure out certain probabilities associated with certain sample means. So, why is learning about the distribution of sample means important? Well, the primary use of the distribution of sample means is to find the probability of any given sample. You want to know how likely it is that your sample comes from or how well it represents a population. Now, in experimental research, if we administer a treatment to the experimental group, we expect a very low probability of randomly selecting a sample that matches the characteristics of our experimental group because the population at large has not been exposed to our experimentally manipulated treatment. So if the sample has an extreme sample mean, right, with a z-score that exceeds 2, that means that that sample mean is highly unlikely, has a small probability of being randomly selected, and in research we would call this a significant finding, meaning that we're confident that the reason that we got this crazy sample mean is because whatever we manipulated had an effect on whatever it was we were measuring. Now that's beyond the scope of this class because we don't do hypothesis testing in here, but I just wanted to give you some context for how probability can be used in research, like when hypothesis testing is used. So now let's look at this example. So is this an extreme sample? If we take a sample of 16 employees from the population, and let's assume it's normally distributed, so we have a normally distributed sampling distribution. So we take these 16 employees, and we give them on-the-job training, and we measure their job knowledge, and we find that their mean is 55. Are we confident that on-the-job training had an impact on their job knowledge beyond the impact that we would, beyond the difference we would expect to see just due to random chance? So we're going to compare our sample mean of 55 to our population mean of 50. And not only are we going to compare those two means, but we're going to compare that difference between the sample mean and population mean to the difference we would expect to see just randomly, or to the standard error, to see if we have an extreme sample mean. And then we're going to look at the probability that you would get a random sample of 16 that had job knowledge higher than 55 if on-the-job training didn't work and any differences are just due to chance. All right, so when we're doing this, we have our sample mean given to us. We need to find the z-score, and then we need to use that z-score to go to the unit normal table. So between the mean and the z, we need to use a formula, and between z and p, we need to use the table. So the first step in this, finding the z-score. And z is equal to the sample mean minus the population mean divided by the standard error. Well, I know my sample mean is 55, and I know my population mean is 50, but I don't yet know the standard error. So I know that I'm observing a 5-point difference between my sample and my population, but I don't really know how much of a difference I would expect to see just due to random chance, even if on-the-job training had no effect on job knowledge. So it's time to find the standard error. All right. The standard deviation for the population is 12, and the sample size that we're working with is 16. So this becomes 12 divided by, well, the square root of 16 is 4, and 12 divided by 4 is 3, so now we know what the denominator of z is. And 5 divided by 3 is equal to 1.667. All right, that's our z-score. So I'm looking at this and I say, well, it's not quite a 2. So we wouldn't really call it extreme. So I wouldn't be really confident that the reason that we got this sample mean of 55 is because on-the-job training worked, because it's just still too likely that we probably could have gotten this sample mean just randomly, even if on-the-job training had no effect. Let's go ahead and draw our distribution because we're going to need to do that to visualize the probability of getting job knowledge higher than 55 if on-the-job training did not work. So, draw our normal distribution. Frequencies are here. We've got our sample means represented here and the z-scores for those sample means. So our population mean is 50, so we put that in the middle because that equals the mean of the sampling distribution, z-score of 0. And we were looking at a sample that had a mean of 55. And we know that the z-score for that sample is 1.667. So if we kind of visualize where that falls in the distribution, it's too high of a frequency. It's still too likely that you would get a sample mean of 55 just randomly, just due to chance, again, even if on-the-job training didn't work. But now let's figure out what's the probability that you would get a mean greater than 55 if on-the-job training didn't work. So we are looking for probability of a sample mean greater than 55. So we took our mean, we calculated our z-score. Now we're going to go to the table to find p in the tail, the smaller portion of the graph. Now you know what? While we're there, let's go ahead and figure out what's the probability that you would randomly get a sample mean from 16 employees that's less than or equal to 55 from this population, assuming that on-the-job training has no effect and our sample still does represent the population. Well, for that one, we'd be looking in the body. So I can go to my z-score of 1.67 because that's what we'll be looking for in the table. Remember, it goes to the hundreds place. And then just look for the body to find the other one. All right, so let's go look at our table. So I'm looking for a z-score of 1.67. And, oh, there it is. This is my proportion in the body. This is my proportion in the tail. So, body 0.9525. 0.9525. And then the tail is 0.0475. And as always, if you add those together, you get 1 because that represents the entire graph. So we're saying that it's highly unlikely that you would get a mean greater than 55 if on-the-job training worked. So it's too bad we didn't get a mean greater than 55. And it's pretty likely that you would get a sample mean less than or equal to 55 from this population on job knowledge, right? That's what this represents, the mean of job knowledge, if on-the-job training did not work. Another example. All right, so this would be a situation where we're using observational research. So in observational research, we can test our assumptions or test claims of others. So how likely is this outcome in this population? Is the reported mean suspect, right? We're testing claims of others. So for this one, Titleist is trying to convince professional golfers to switch their brand of drivers with the claim that a golf ball hit with their driver travels a mean of 295 yards with a standard deviation of 15, and this would be out of the entire population of all 600 professional golfers. This is the claim that they're making. Let's say that we take a simple random sample of 36 professional golfers, and we find that their average drive distance is 285 yards. Well, on the surface, you might be led to believe that because 285 is less than 295, that the claim is not supported. However, this 285 is based on a sample. And we know from the concept of sampling error that we really never expect the sample mean to equal the population mean. So, the sample mean could be higher or lower depending on chance, but not due to actual differences caused by the brand of the driver. Maybe you've just randomly sampled professional golfers with less power in their drives. So, the sample mean can be slightly lower than 295 and still support the claim. So the question would be, really, we want to know, is this an extreme result? because we're going to compare the actual difference to the difference we would expect to see just due to chance, even if Titleist is being honest. Because remember, we're expecting differences randomly. So the question is this difference larger than the difference we would expect randomly? And if it is, then we are going to question this claim made by Titleist. Okay, so just like before, to figure out if you have an extreme sample mean, you need to compute the z-score, because the z-score compares the observed difference in means to the difference expected just due to chance to see if the observed difference is much larger or extreme. So we take our z-score by finding, all right, we've got our sample mean minus our population mean divided by the standard error. And the sample mean is given to you, it's 285, and the mean of all golfers is 295. I do not know what my standard error is. Time to figure it out. So standard deviation divided by the square root of the sample size. My standard deviation is 15, and my sample size was 36 professional golfers. So this becomes 15 divided by the square root of 36 is 6. And 15 divided by 6 gives you 2.5. So we would expect, with any given sample of 36 golfers, we would expect their sample mean to be off by about 2.5 points just due to random sampling error, just due to chance. So the question is the observed difference, the 285 minus the 295, substantially larger than the difference we would expect to see just randomly? And if so, then maybe this isn't accurate, right? We wouldn't be likely to get this sample randomly if this was true. All right, so 285 minus 295 is negative 10 divided by 2.5. And we get a whopping z-score of negative 4. So what this tells me is that the observed difference between my sample and my population is 4 times smaller than the difference we would expect to see just due to chance. So at this point, I'm not feeling too good about Titleist's claims, because if we drew this out, and again, I'm representing my sampling distribution, which represents the frequency or the probability. You can think about probability as well, because probability is based on frequency, of every single sample mean of 36 that could be drawn from this population just due to chance. So if we're looking at this sampling distribution, the mean for the population is supposed to be 295. The z-score for that is 0. And with our sample mean of 285, we get a z-score of negative 4. That's like way out here, right? This is in a really low frequency part of all the possible sample means that you could get if Titleist's claim was accurate. So let's go ahead and figure out, how likely would it be to find a sample mean of 285 or less if Titleist's claims were accurate? So probability of a sample mean less than or equal to 285. So we need to find the z-score of 4 to figure out the proportion of means in the tail, right? This is a tail situation. All right, so let's find 4 in our unit normal table. Remember, there's no negatives, but it doesn't matter because negatives and positives are as long as they're the same absolute value, they're the same distance from the population mean. Z-score of 4, proportion in the tail, 0.00003. Oh my goodness, it's almost impossible. So 0.00003, or if you multiplied this by 100, 0.003% chance that if you took a random sample of 36 golfers, they would have a drive that's less than or equal to 285. So now I'm even more suspicious of Titleist's claim. All right, so this next one, I want you to pause this video and try it on your own. So pause it and give it a shot. Figure out the probability of randomly selecting a sample of 2 with a mean greater than 5, and the probability of randomly selecting a sample of with 30 people in it with a mean greater than 5. Okay, so hopefully you went through and you figured this out on your own before watching this video with the answers. So, all right, we've got two different scenarios. Let's call this scenario A and let's call this scenario B. So we've got a situation where we have 2 in our sample and a situation where we have 30 in our sample, but we're still working with the same population that has a mean level of job satisfaction of 4 with a standard deviation of 1. And we're wanting to see what's the probability of randomly selecting a sample with a mean greater than 5, or in this metric, more than somewhat satisfied, from a sample size of 2 versus a sample size of 30. So the first thing we need to do, and let's go ahead and put part A over here and then group B over here. Let's draw like a little line. All right. So this is when n equals 2. This is when sample size equals 30. Alrighty. So the first thing that we need to do is we need to figure out, because remember we're going from a sample mean, we need to go to Z to then find P. So we need to find our Z-scores. And in both cases, Z is equal to the sample mean minus the population mean divided by the standard error. So just write my formula down. Keep everything organized. All right, so my sample mean and my population mean are the same for both examples. We're still working with a sample mean of 5 minus the population mean of 4. The only difference is going to be the standard error. And at this point, you should be able to tell me which z-score you think is going to be larger. Think about it. That's the same thing as me asking which standard error is going to be smaller, right? So the larger sample size is going to give us the smaller standard error and a larger z-score. But let's go ahead and solve for this just to confirm that. So my standard error when I have a sample size of 2 is equal to, so the standard deviation divided by the square root of n. The standard deviation is equal to 1 divided by the square root of 2 becomes 1 divided by 1.414. And 1 divided by 1.414 gives me 0.707 for my standard error. Let's find the standard error for a sample size of 30. And I already know I'm expecting this to be smaller because I have a larger sample size. So same formula as before. Same standard deviation, but now we're dividing by the square root of 30. And this becomes 1, so the square root of 30. So 1 divided by 5.477. And 1 divided by 5.477 gives you 0.183 for your standard error. And yes, in fact, it is smaller than the standard error for a sample size of 2. So now we can plug our standard error into our z formula. So I'll do the one for a sample size of 2 first. So 5 minus 4 is 1 divided by 0.707. And you end up with a z-score of 1.414. Then over here, for the sample size of 30, 5.4 divided by 0.183, 1 divided by 0.183, and you get a z-score of 5.464. All right, so we want to know the probability of randomly selecting a sample with a mean greater than 5 when we have a sample size of 2 versus a sample size of 30. So let's go ahead and sketch out our distributions first. Got our frequencies here. We'll represent our sample means and our z-scores here. And we've got our normal curve. All right. Our population mean is 4, and that has a z-score of 0. And we're looking at a mean of 5. And we know that 5 has a z-score of 1.414. in this case. Now let's draw the sampling distribution over here, and I'll be careful to try to draw a more narrow curve because our standard error is smaller. Okay, so we've got our mean of 4 from our population, and we're still working with a z-score of 5, or yeah, a mean of 5, which is like out here, and it has a z-score of 5.464. So when I sketched this out, I tried to visualize the fact that I have a larger standard error here and a less extreme z-score for my sample mean. So my sample mean falls in a more frequent part of the distribution. Whereas here, I have a smaller standard error and my mean is more extreme, has a larger z-score, and it falls in a lower frequency part of the distribution. But in both cases, if I'm looking for the probability of getting a mean greater than 5, I'm looking at a tail. It's just the tail for a sample size of 30 is smaller, so I'm going to have a smaller p-value because it's going to be associated with a larger z-score than when I have a sample size of 2. So let's go to the table and look for 1.41 z-score and then find the proportion in the tail. So z-score 1.41. Oh, I missed it. 1.41, proportion in the tail, 0.0793. 0.0793. So it's pretty unlikely that we would get a sample that was more than somewhat satisfied from the population, even if our sample size was only 2. Now let's take a look at finding the z-score of 5.46. Well, guess what? It's off the charts. This table only goes to 4, and look at the probability in the tail for a z-score of 4. So, in this case, even though we don't have an exact value, if you did this in a statistical software program, you would. But with the table, we can basically say that the probability, and since we round to the thousands place, we'll just say less than 0.001. It's pretty much impossible that you would get a sample mean greater than 5 from this population when you have a sample size of 30. So we could say it's much more likely to sample 2 U.S. workers with a job satisfaction greater than 5 than it is to sample 30 workers with a job satisfaction greater than 5. Because the larger sample results in a lower standard error, the mean difference of 1, right? That mean difference of 1 is considered more extreme and less likely in the larger sample compared to the expected mean difference, or compared to the standard error. So you think about it. You expect larger samples to be more representative of the population, so you would be expecting less likelihood of getting any kind of mean difference compared to a smaller sample, which is less representative of the population, and you would expecting more of a mean difference because your sample is less representative of the population. Okay, so I hope that those examples helped you understand how to use the unit normal table when we are talking about the sampling distribution and finding the probability associated with any given sample, and help you understand standard error and how it's impacted by the standard deviation of the population and the sample size.